Influence of functional groups in biological activity. We are going to talk about the different biological activities. Influence of functional groups. Well, when we talk about functional groups, first of all, we have to remember some very basic things. We are talking about a particularly heterolytic group. Most of the time, functional groups, almost in all cases, are formed by heteroatoms. That confers the molecules their physical chemical characteristics. And by implication, or in parallel to that, confers the molecules their characteristics of reactivity. Then you will say, I have to know the functional groups. I have to review that again. That at some point I saw in organic chemistry. Yes, I'm sorry, you're going to have to know it. Already know some basic properties of these groups. So we need to know some basic functional groups, because they are responsible for the physical chemical properties of the reactivity of a molecule. And we have to remember the following. When we talk about a bioactive compound, that is, a compound that is designed to be managed by a human and cure pathology, this molecule has to be able to go through the lipid layer, because most of the time the molecules are managed by oral life. So it means that it has to be absorbed at the intestinal level, sometimes even at the stomach level. Rarely we inject the drug directly where the problem is. That happens in laboratory mice, only where it's injected right in the tumor or whatever. But at a human level, that is very rare that happens. Imagine a problem at the brain level. How are we going to be injecting directly? And it is difficult. Then the molecule has to have certain characteristics that allow it to go through a lipid layer. And here I am going to introduce a concept, which is the concept of lipophilia. It appears like this in the text. It also appears as hydrophobicity. Exactly. Lipophilia, hydrophobicity, lipophilicity. I have also seen out there, the most common is lipophilia. That is, the molecule has to have an adequate ability to solubilize itself in lipids, but not much, in such a way that it can go through the membranes. And here is the structure of a membrane. We are going to go gradually forward in this. The structure of a membrane, you know that it is a lipid layer, where the polar part is in the center of the membrane, or outwards. And well, this would be inside the cell, right? Is it towards the ends or towards the center? Very well. It is not true that it is always outward. Very well. And towards the inside, that is, in contact with the water. So we have this amphiphilic property. We have contact with the water from the outside, from the inside, and towards the center. There are the hydrophobic chains. That is, here we have a phosphate group connected to an amino group. And this group is polar because it has oxygen. And the entire hydrocarbonated part is a polar or hydrophobic. So here we have these concepts of hydrophobicity, hydrophilic head. Therefore, our compound must have an appropriate lipophilia to go through membranes. It has to be able to cross barriers, but not so much in such a way that it is retained in the membrane. So there I am going to introduce this concept that we are going to define immediately. I am going to insert a page for it. What is the concept of log? That is the lipophilia of which we are talking. The lipophilia or log. Where, what is P? Excellent, right? How much solubilizes the molecule? Very well. In octanol phase versus in water phase. And this distribution, those square parentheses that you see there, that is molar concentration. How much of the molecule is solubilized in octanol? How much of the molecule is solubilized in water? Octanol and water are immiscible. Octanol is an alcohol and is not miscible in water. Now, why octanol? Exactly, very well. That is, it imitates what? It imitates a membrane phospholipid. Perfect. There we have the structure of the octanol. So we have precisely what we are talking about. A hydrophobic or lipophilic tail. That would be the hydrophobic part. So we have precisely what we are talking about. A hydrophobic or lipophilic tail. That would be the hydrophobic part. And of course, a hydrophilic polar head. This polar head, as you know, is a hydroxyl group, or alcohol in more generic terms, because hydroxyl can be part of an alcohol. It can be part of a carboxylic acid. It can be part of an N-hydroxylamine. It can be part of a phenol, etc. So, in more specific terms, the hydroxyl group, in this case, is part of an alcohol. Well then, the octanol is imitating a membrane phospholipid. This distribution has also been done. When one wants to simulate brain partition, instead of octanol, and this sounds a little weird, it causes surprise when one mentions it. In addition, this partition can also be done with olive oil. Although it sounds like homemade or handmade, what happens is that the olive oil, it is not soluble in water either, obviously. It imitates the lipophilia of the brain quite well. So sometimes it is distributed in high-purity olive oil water to see if the molecule has a tendency or not to go to the brain. We are going to see the use of some platforms where you will be able to calculate this. I will show you later towards the end of the class. So that would be P, C, and since P is going to give us a very large number, these are divisions of molar concentrations, is that we apply the logarithm on base 10 to generate a smaller and more manipulable number. So logP is the logarithm of this width, which, in the best of cases, should be determined empirically for each molecule. But how to determine this empirically for each molecule can be a bit tedious. Today, it is calculated. Today, the log P value is calculated. So let's introduce another idea there. We just said, I'm going to separate this here. We just said that for the compound to be a good compound, it has to go through membranes. That is, ideally, the log P value. The ideal log P value. The log P has to fluctuate between 0 and... Christian, do you remember how much it was? More or less? The maximum value. There's a maximum value that is 5. Exactly. Yes, we are going to enumerate it now, so that everyone has the complete information. From 0 to 5, you will say, where does that come from? Who came up with putting these limits? Because the log P can be seen at values much higher than 5. So that is our limit. And this comes from a statistical analysis. This is nothing more than statistical observation. What does that mean? It means that the lipophilia of almost all the molecules that are drugs were reviewed, and most of the ones that are absorbed well by the oral vein, that is, they can go through biological membranes at the intestinal level, they are below 5. The ones that are very lipophilic are absorbed little. They are retained in the membrane, that is, in the intestine. I'm going to give an anti-parasitic example. Look. We will consider the following molecule. We will consider this compound. We will consider this compound. And this compound, as simple as it seems, is an antiparasitic. This compound is made to kill parasites, that is, worms, that infect the intestine. And this molecule is super lipophilic. And it is not absorbed, it is absorbed very little at the intestinal level. But that is good, because we want to kill parasites that are in the intestinal lumen, not parasites that have entered the blood plasma. Therefore, in this case, we have a molecule that has a log P greater than 5. Super lipophilic, it is absorbed badly, but that's why it's fantastic. It is occupied because it stays there in the intestine to kill parasites. Antiparasitic or antihelminthic is the other name that has this type of structure. Later, we will see concrete examples of this type of family, with this type of pharmacophore in particular. Let's go now to the logP issue. This logP value that ideally decreases to 5, so that I have a good oral absorption. What is here is for the compound to have a good oral absorption. I use some software to obtain this information. Allow me a moment here to adjust the image. I'm going to show you this alternative. Although there are many others, this program is called ChemDraw. It is from Sweet Chimoffice that you can also get to install on Windows or other platforms. And this program has the particularity that not only serves to draw, but to calculate some things. So for example, if you are interested in that molecule, in that anti-helmintic that we were just seeing, we draw it. Well, here the double is going there. So if in some work that we are going to do in the semester, we need a logP, and we are going to see that the logP is very necessary for many things, particularly to do CUSA studies, which is one of the topics that we are going to study in this course. So very likely, we are going to be going to the logP and to other values. Well, apart from drawing, you come up here and we can ask for values, show off certain properties. Let's see. And that was in Show Chemical Properties window. There is this option. Give us a click, and it loads us here. Now we paste. I'm going to close this, and it automatically calculates us from a database of fragments. Through mathematical algorithms, we obtain several values. For example, the boiling point, the melting point, etc. And if we go down here, the closest value to reality. Because this is calculated, this is not real. It would be this one that says C, this C of calculated or ChemDraw logP. This value takes up a lot. It is a good approximation of the lipophilia of the molecule. It is already a high lipophilia. It does not reach 5 here, but it is a lipophilia that in this particular case to this compound, it does not allow a good absorption by oral path. Almost 3.6 of C log P. So C is the computing algorithm. So this is a way to obtain the lipophilia of a compound through a simple calculation with ChemDraw. Another strategy, if someone says, well, but I can't install that software or whatever, the second alternative. And this tool, I insist, we are going to occupy in this semester. That's why I'm delivering it here. The second strategy is one called pre-admit. And I'm going to see if it works for me from here. They'll pre-admit. Because sometimes the university blocks us here. Certain connections to the foreigner. In particular, this server is in Korea. So pre-admit, all this is free. Let's see if it works. It works like Swiss admin. Exactly, of course. We can go there. What does that mean? I have it there. Yeah, super. This admin. Yes, we are also going to enter it. Here it is loading, fortunately. Super. Well, here we have several alternatives to calculate, for example, drugability. This word is a term that has been coined lately. Drug-likeness, this did not exist before. It means drugability. That is, how much probability does a new molecule have of having some kind of irrelevant therapeutic activity. That is, if you, for example, say, I want to know what the properties of acetic acid are. That does not have drugability in such a simple molecule. Acetic acid is the acid component of vinegar. That will not have any bioactivity, I understand. That is, it is not drugable. It does not have drugability. A new term that has been coined. Here we have absorption, distribution, metabolism, and excretion. This is super important. It is called ADME. It is an abbreviation of what is pharmacokinetics that we are going to define later. And we can also calculate toxicity. Well, but we go here to ADME. Absorption, then there it is. It is absorbed. It absorbs us. How will its lipophilia be? Let's see if it gives us a value, because it also delivers a list of things. So let's do the quick calculation of the same molecule that we have here. Probably one can copy this molecule and paste it there already in this particular format as smile. But it does not have. We are going to draw it then. Let's see some of the interesting things that this between. Oh, sorry. Well, let's see. Yes, there it is. Already. Okay. Okay. And yes, we press the button there, submit, and now wait. It does not take so long, obviously a little slower than using the ChemDraw installed on the computer. But a couple of seconds, here it is slow. In other parts it throws it much faster than the connection. Here maybe it is not the core. There I throw the thing. Look how interesting. The barrier. Exactly. These 3B, that's not good, nice and cheap. But it is encephalic barrier transfer. As you can see, there one expands and the meaning appears. Concentration that reaches the brain, divided by the concentration in plasma or in blood. It says here 3. That is, if this value is 3, it concentrates 3 times more in the brain than in the plasma. That is, if this molecule we inject it, it will be absorbed into the brain. Why? Because it is so lipophilic that it easily crosses the brain. Well, let's see other value. Solubility in buffer. That is, we can know how many milligrams per liter. We can solubilize this in a very useful buffer. In biological experiments, we can see the transfer through the skin. We can see if it inhibits or not. We can see that it inhibits hepatic cytochromes. Therefore, we can see interaction with other molecules at the hepatic level. This is very useful in human pharmacokinetics. We can see if it inhibits or not glycoprotein P, which is a glycoprotein that expels drugs out. And therefore, it is not true if it is a substrate of glycoprotein P. That is not good. And let's go to the lipophilia. Let's see if it's there. Let's see. Here it is. Now it's called SK because it's another algorithm of calculation, but it's logP. If you expand it, it says what it is. There's a calculated logP value, do you see it? And a prediction, 2.95. Do you see that the value is different? Because it will depend on the calculation algorithm that one occupies. We also have this platform to have an approximate value. Always the approximations will have those ranges of difference. It will never be the same as empirically calculating. There is another way to calculate that it is not dissolving noctinol and water in an agitator funnel. Nowadays, it can be done by other techniques, particularly by HPLC. There are HPLC techniques to experimentally calculate logP. And the last thing, I will not calculate so that we do not waste so much time with this. But yes, the other link that Christian had given here is the Swiss Army. It's also free. And also, at some point, we will enter there. And we are going to obtain some relevant information from the Swiss Army. And this is not. And there he is a Swiss server. So you, from your homes, access it, curiosity, draw a molecule and calculate something. And there you will see that many values appear. And at some point I will give you, maybe from the phone I can give you Wi-Fi. Because yes, it will help us to illustrate some things. Because the Swiss Army has some graphics different from the Priad Med. Well then, returning to our note. The individual or the organization that determined this range was the North American pharmaceutical company Pfizer, particularly a researcher named Lipinski. So we have what today are called Lipinski's rule. Lipinski studied huge databases of thousands of molecules, and for something to have a good oral absorption, he found following. So a good or appropriate oral absorption. It is characterized because 1, the compound is going to have, as we have already seen, a log P5. And this is statistical. Remember, there are always exceptions. And nowadays, there have been several exceptions to Lipinski's rules. And second, a very large molecule is not going to be absorbed well. They usually have molecular weights less than 500 grams mole. As you can see, this is empirical. There was no way to predict that. There are exceptions, of course. Today, there are many exceptions, and this is being reviewed because giant molecules have been found that break Lipinski's rules. For example, you know that at the intestinal level, there are transporters. Amino acids, when one consumes amino acids, are absorbed by protein transporters. They do not go through passive diffusion. They are small molecules. They are very polar. So how do they go through a polar membrane? By protein transporters. Third, a molecule with good oral absorption has less than 5 sources of hydrogen. Less than 5 sources of hydrogen. When I say sources of hydrogen, we come to intermolecular interactions, thematic that we are also going to address in the course. And we talk about strongly polar groups such as O-hydroxyl or NH, that can be NH of an amino acid, etc. And then less than 5. That is, we are quite limited because what is the point? Well, this is also hand in hand with the next T. We must have less than 10 bridge acceptors. And when I say less than 10 acceptors, they are all those atoms that can accept a hydrogen bridge through a non-linked electronic pair. Like, for example, an oxygen that has an electronic pair available to accept a bridge through a non-linked electronic pair. For example, an oxygen that has an electronic pair available to accept a bridge through a non-linked electronic pair. For example, an oxygen that has an electronic pair available to accept a bridge of hydrogen, a non-basic nitrogen, that can accept a non-basic interaction. You will say, why is that? Because if it is basic, it will protonate. P7 will act with a positive charge and something positive cannot interact with a more positive proton delta. There are other less common hydrogen bridges, such as fluor, when it is a bioactive molecule because fluor does not exist in amino acids. And there has also been a hydrogen bridge with more rare atoms, although they are weaker and specific, such as chlorine and the sulfur. A phosphor could even participate, yes, but I will leave it written because theoretically it is correct, but it is very rare to find a drug that has phosphor in the structure. There is, but rare, because phosphors are supertoxicox. They tend to generate toxicity with many enzymes, and we are going to see some mechanisms of toxicity. Phosphors are oxophilic and tend to covalently link to proteins. Well, then these are the famous rules of Lipinski, and today they have been adding more things. For example, it has also been seen as extra rules, so to speak, that ideally we have to have what is called a molar refractivity, or Mr. minus 500 E. This is a concept probably new for you, the concept of molar refractivity. Well, what is this refractivity? I do not know if someone sounds sound. It has nothing to do with something. Let's say it sounds like something broken. I imagine something that is going to break. No, it has to do with And of course, what it's going to do is that to calculate it. one calculates what is called the refractive index of light on the molecule in the aqueous phase. But of course that is to obtain the number. But the concept, and how good that you made me the observation, the concept is much broader and has to do with the following. Molar refractivity always delivers two things. First is a measure of the volume of the molecule. It is a measure of the molecular volume. And second is a measure of its polarizability. That is why when one goes to the textbooks or to the handbooks and finds the values of calculated refractivity or measured for several molecules, the units of the, let's say it like that, right, of molar refractivity or units of volume. Okay, units of volume, and many times it is expressed as molar volume. So, the more refractive the molecule is, the easier it is to polarize. That the electrons move from one side to the other, generating accumulation of charge in one part, and low deficiency in another. That is the idea, a little abstract, that you have to have with this concept. I know it is not as concrete as the LiPo, but we could say that, for example, large atoms like halogens. For example, a large chlorine atom connected to the rest of the molecule. Large atoms have a high polarizability and a high volume. Large atoms have a lot of molar refractivity. Why? Because as they are large, electrons can move from one side to the other, and that will explain to us the halogen bridge that they make when we see intermolecular interaction. So let's go now here, so you can see that we also have this data in this type of calculations. Look, here for this same molecule that we were doing the molar refractivity. If we go down, the calculated value is very high. Look at 5.9. That is, it is almost 6. Now, sorry, I told you 500. Let's see. It's 5. I think I told you 500. I don't know where the point is. Rectify it. 5. There, yes. Though in this case, 5.9 is a high refractivity. It will not have very good absorption, you see, and we already know that it is acting at the intestinal level. And let's do the next exercise. To the same compound, we are going to connect a large and voluminous atom. For example, an iodine atom. A large halogen. The iodine is super large. Chlorobrom and iodine are giant halogens. The fluoride is the only one that is small, similar to a hydrogen. So, let's go here to view, and we tell it to give us the properties here. Chemical properties, enter, and paste. How much do we get now? Yes, it was clear, 7.2, and only by introducing an atom. An atom makes a brutal difference. They would tell you, well, let's not put halogen on it. That it is not like that, because we are going to see that when we make drug designs, and we are going to do some docking workshop. There you will see that an atom changes everything, and sometimes one needs that atom. I don't know if everyone knows that Christian was doing docking. 300 of molecules, and sometimes one needs a particular atom. And a chlorine, a bromine, a iodine can change everything, okay? So of course, there unfortunately the pharmacokinetic property goes a little bit zero absorption by oral way. Well, let's go back to the appointment. And with that in mind, now we can move forward a little more. Regarding what we have here, the transport of the bioactive compounds. It will be, for example, as it says there, through passive diffusion. You have this, I shared it with you. So we are going to have to pass the membrane passively. That is one way, but there is also facilitated diffusion. If we mark down here facilitated diffusion through protein, yes. Oh no, in the mail. Yes, of course, please download there from the mail. I can support it in the classroom already, but in the mail it is already. Like the program. Okay. And here we have the Fick's law, which is a mathematical equation that describes, as it says there, the variation of the concentration through a membrane, through the course of time. So it is nothing more than a small equation that describes the movement of the molecule, how it spreads from one side to another through time. When we have a difference in concentrations from one side to another, as the variation of the concentration through time by the membrane is equal to the area of cross diffusion by a constant, and these would be the concentrations on one side and the other side of the membrane. That is, let's say it like that. It is not true. On one side, it could be the extracellular. On the other side, it could be the intracellular. But I'm going to return to this equation later because when we see causal, I have to show you how from the diffusion equation, we got to what is called the Hansch equation. So I'm not going to go too far yet. And the question that arises now. And as we have this tool to calculate the lipophilia of a molecule, we can in some way also, without such complex tool, be able to predict the solubility in water of a bioactive compound. If it is a natural or synthetic compound, we have this table with these values. I'm going to increase so that it looks a little better. That shows us how a simple functional group can increase the solubility in water. So number one, it says here, ammonium, which would be a nitrogen with permanent positive charge, or carboxylate, which would be a protonated carboxylic acid. According to this, it is capable of dissolving up to 6 carbon atoms. Now please, this information that is in this table, again, these are statistical values. Therefore, these are averages. It always has its exceptions. Example, look, we are going to immediately place some molecules to illustrate this. One, two, three, four, five. 1, 2, 3, 4, 5. This compound, as it is there, would be pentyne. And that is insoluble in water. That is a liquid insoluble in water. Two phases are formed, such as water with oil, if one joins. But if you transform that pentane and do this, introduce a carboxylate in the structure. When I say carboxylate, we are explicitly saying that it is 100% ionized. And maybe today we are not going to achieve it, but the other class, if we are going to do mathematical calculations of ionization, it is 100% ionized. It is different from drawing the molecule in this way. 2, 3, 4, 5. Draw the molecule in neutral form. It is not the same solubility. If you have the compound in the form of a salt, this would be the compound in the form of a salt. It is more polar. It is more soluble in water than if the compound is neutral. So be careful with that. Yes, I know what you were going to tell me. The acid is easily ionized. It releases easily. Yes, but I have to form the salt. When I form the salt, this group becomes superpolar. And what do you think? The molecule is now soluble in water. In other words, just by retaining that information, you can predict how soluble water is going to be a molecule. That is exactly the idea. What happens now? Already using this same structure that had 5 carbon atoms. Remember that one has a carbon atom. So it would be 2, 3, 4, 5. That group we said was called carboxylate. And specifically, well, this would be carboxylate. Whenever we see this group with double link, That single group by itself, Ni. It is part of the functional group, but by itself, we are going to call the carbon group. I am trying to remind you of things that you saw at some point in organic chemistry, and that now we need it, because we are going to be always talking in technical terms. We are not going to be making that little piece from there, but with technical names of each functional group. And look, now this same molecule. We have 2, 3, 4, and I'm going to leave it there, and we're going to do it ammonia now. Sorry, I would have to erase one more. There, 1, 2, 3, 4, 5. It's 5 carbon. There, I have 5. 1, 2, 3, 4, 5 carbon. This would have a positive net charge. That is a quaternary ammonia. Quaternary, because it has 4 carbons together with iron. It has this, which is a methyl, methyl, and methyl. Quaternary ammonia cannot lose its charge because it is always positive. Quaternary ammonia is always positive because to lose the charge, it would have to lose a methyl and recover the electronic pair, and that is not going to happen spontaneously. So this compound with this ammonia, even though it has 5 carbons like the pentane, it is 100% soluble in water because an ammonia can dissolve up to approximately 6 carbons in total. That has the structure. So this is also 100% soluble. 100% soluble in water. So it's very simple things we can understand a lot and predict. One of the objectives of medicinal chemistry is to predict things. Let's go to the second case. It says with alcohol 2. Here the most relevant groups are these two, a carboxylate, an ammonia, and alcohol. The hydroxyl that can be part of an alcohol or a phenol. That is, it can be connected to an alkyl chain or to an aromatic ring. 3 to 4 carbons, then it dissolves less. You, a good 3 or 4, is that has a statistic. This is not true, an approximate value. Sometimes we can fail in our predictability. 3 or 4 carbons. Look. Let's see, what do you think? This compound that I'm going to draw here, it's called tetrahydropyranone. This is the tetrahydropyranone. And here you think, is that soluble in water or not soluble in water? That is not alcohol. It is not, oh, you are seeing, oh, it has less polarity. It does not have the proton. So what do you think? 100% soluble or 100% insoluble? It does not have carboxylate. It does not have ammonia. And oxygen, 100% insoluble. But let's do the next transformation. I'm going to draw it this time with a little perspective. The profile, let's say. And I'm going to do what is called a Haworth projection. As is. In fact, specifically, this one that we are drawing here. This is glucose. We have not changed much, only that we have one more carbon in the structure, because there we would have 1, 2, 3, 4, 5, 6. In the previous one we had 5, right? 1, 2, 3, 4, and 5. So the only difference is that there is one more carbon, but it is full of hydroxyl groups. And glucose is soluble in water, of course. We all know that this sugar is soluble in water. Even the sucrose, which are 2 sugars connected soluble in water, which is the one that sweetens the tea. So glucose is 100% soluble in water. Why? Because it has hydroxyl. And a hydroxyl. Suppose that a hydroxyl. Let's go for the low part. A hydroxyl solubilizes 3 carbon. And then how much could theoretically be solubilized by all that? Because we have 1, 2, 3, 4, 5, right? This is not enough to be, but it is similar. 1, 2, 3, 4, 5, 5, 4, 3, 15 carbon. 15 carbon, and perhaps a little more for that, although that gives us a lot. 15 carbon. And it is not enough because here we have 6 carbon. So you see, so one can predict. So there we can see that a molecule, as simple as the first one, it is not soluble because it does not have polar groups, but the other one does, because it can be solvated by water. So the explanation of this is that what happens is an extensive solvitation. Water forms hydrogen bridge. This is the total solvitation. That is in parentheses, that means that water forms hydrogen bridges with the compound. Now, a very polar molecule, very full of groups. So they form a hydrogen bridge with water. That has no solubility in fat. Will that molecule be well absorbed by the intestine? A very polar molecule? Neither. A very polar molecule is not well absorbed. But glucose is absorbed 100%. Because at the intestinal level, there are transporter proteins that absorb glucose and take it inside. Then you notice that there are transporters that you have to take into account if it is a different transport. But when we talk about Lipinski, we are always thinking of passive diffusion. By passive diffusion, that bounces. It does not happen because it is too polar. And on the other hand, if something is very lipophilic, it does not happen either. It is retained in the membranes. Such lipophilic that has stuck adheres to the membrane without managing to pass the membrane. And then we have, it says, an amine. Well, this is an incorrect way of drawing, because in stricter over, this would be imine. It says an amine, a carboxylic acid, but neutral or an ester, which is also neutral. It says more or less 3 carbons. What I'm going to tell you is that from here down here, the bad solubilizers come. Amine and carboxylic acid solubilize more when they are ionized. The ester will never be able to ionize. The ester can be hydrolyzed, but that is different. Let's see. Let's go first to these 3 groups to remember some very simple things. Around, I would say, about 90% of the bioactive compounds, whether natural or synthetic, they are amines. So this group is super important when it comes to a natural compound, specifically when we talk about a compound of natural origin. And one says that natural compound has amine. There, the classification of that compound is alkaloid. An alkaloid is an amine of natural origin, that is, a secondary metabolite. Nitrogenated basic. An alkaloid, by definition, is a secondary metabolite. A secondary metabolite is part of the secondary metabolism of the plant. It is not part of the metabolism of glucose, of adenine. That's what I mean. It is secondary metabolism. It is part of the secondary metabolism of the plant. Many times they are produced in large quantities. And alkaloids have some kind of hide, acid nitrogen, in the structure. An alkaloid is a very common bioactive compound. Very common. Alkaloids are taken out of plants. Of marine algae, it is also very common to look for alkaloids, in contrast to other types of natural molecules, which are terpenes, which we will also see in a while. Well then, amines can be primary, secondary, or tertiary. We could have, for example, this amine. A is the rest of the molecule. Primary amine. We can have a secondary amine, or we can have a tertiary amine. So what do you think? Which is more polar? Perfect. The first one because it has two protons, easier to form hydrogen bridges with water. Very good. Then the first one is the most polar. Do not confuse this classification. I'm going to move the sheet a little bit with that of alcohols. When one has primary alcohol, one has this. This is primary. A secondary alcohol. The alcohol will always be the same. It is the carbon that is changing. The carbon that has the alcohol and a tertiary alcohol. It is joined to a carbon that does not have. It is the carbon that is changing. The carbon that has the alcohol and a tertiary alcohol. It is joined to a carbon that does not have hydrogen. So it is different. Do not confuse primary, secondary, and tertiary alcohol with primary, secondary, and tertiary amines. The structures are different. Here, the one that is losing protons is the nitrogen. Here, the one that is losing protons is the carbon that is connected to the alcohol hydroxyl group. So we will also repeat this type of structure. So primary, secondary, and tertiary amines, and primary, secondary, and tertiary alcohols. They are very common functional groups in medical chemistry. Do you remember how much it could dissolve? It said one amine. Of course. We are going to round more or less 3. And the same, said the hydroxyls. We are going to round more or less 3. The amount of carbon that is achieved only, now, again, I repeat. When it says here, more or less 3, it is always considering that this is not ammonium. This is neutral, because if it is positive, there we go to this other end. Excuse me, what does this move? Where we had the ammonium. How much dissolved? Up to almost 6, I think it was. A positive nitrogen, whether it is ammonium or permanently positive, or ammonium formed in the middle. That is, it is protonated. It will dissolve up to 6 carbons approximately. Super good observation. There we enter the final weapon. What? Contrayon affects solubility. It affects solubility in what is called deposit preparations. That is a very good observation. I'm going to illustrate it here. First, when one has to prepare a drug, in the form of salt, the question is that contrayon occupy example, look. It is a molecule that is occupied for epilepsy, which is this. Let's see, we would have 1, 2, 3, 4. There it is then, 1, 2, 3, 4, 5. This compound is called valproic acid. It is one of the most used drugs for epilepsy due to its lower cost, to its low toxicity. And this compound is in anionic form. Here we are going to remember some small things. I'm also going to send you some exercise guides. Do not forget that negative charge, it is the same in both oxygens because we have resonance. Then you will say, I have to remember all those things. And unfortunately, you have to remember some of these little things. Then yes, here we have. That is in resonance. Then the charge is dislocated equally in both oxygens. That the charge is in both valproic acid. Then we have the possibility of formulating it as salt. You will say, and why bother? Well, one formulates a salt most of the time because one wants to improve the stability of the compound. That is one of the main reasons we formulate a compound as salt, to improve its stability. And when I say stability, is that the molecule is more resistant to moisture, to light, to oxidation. That is, that it lasts through time, and that it does not decompose easily. Another reason why one often wants to formulate a salt is when one wants to improve its solubility in water. I mean, I want the compound to have some solubility. In water, for example, if this was as permanent salt. It would be 6 carbons that would be able to solubilize. We are short, right? Because we would have 1, 2, 3, 4, 5, and we go 6, 7, 8 carbons. So no, it will not be 100% soluble in water, okay? Well, the question is, what compound to occupy? We could occupy as a compound, for example, as it is quite negative, well, a sodium could be. So there is a pool of options. We could occupy a sodium, but we could also occupy a potassium. So does it give the same? No. It turns out that the solubility in water changes when the compound is decomposed. In the decomposing process, the solubility that it provides with a compound is different from the solubility. It is different from the solubility with another compound. Second, potassium is usually more expensive than sodium, so also the economic reasons of what salt to occupy. And third, in some cases, it is also preferred the use of organic salts. Yes, let's go to. I am going to put it here. Organic salts. Die Kurzstay. Und it is often preferred the use of organic salts. Let's see. Let's see. The next case. Well, here, that is there connected by another carbonyl group. Here I would be missing. Let's see. I would have 1, 2. I think I'm missing something there. Let's see. It would be 1, 2, yes, carbonyl. There. 1, 80. This compound that is here has the possibility of existing as organic salt. First, some observations. Excuse me, I have to move there to explain something, or else I can reduce it a little bit. Look, this compound, when we mark this blackened, it means that it comes ahead of the plane of the board. It comes ahead of the plane of the board. That is, the carbon that contains it. There is a chiral carbon, and this carbon would be therefore absolute configuration of type R, okay? This is an absolute configuration carbon of type R, and the other side is also chiral. So here we have to say that if this comes forward, in this case of the plane of the board, that is to say, how does that know? What happens is that that molecule, this is a compound of natural origin, and it gives them a certain similarity to something. It reminds them of something. Look, when one sees, and that's what I want you to learn in this course, that you retain certain structural motifs. When one sees this square system here, well, this square system that you see here, functionally, let's see, ask, what functional group is this? Very well, it's an amide what? Cyclic, and cyclic amides are called lactam. That is a lactam. It is a lactam that has 2 carbon. It has an alpha carbon and a beta carbon as part of the square cycle, okay? So if I say I have a lactam, an alpha beta lactam, that is, I have what is technically called a beta lactamic ring. Oh, no, yes. Antibiotic. This is an antibiotic. This is penicillin. So when we have penicillin, we have this nitrogen, and this nitrogen is not basic. It is not protonable because it is an amide. It is an amide nitrogen, and therefore the electronic pair does not protonate. The same here. This nitrogen is not basic. It is not protonable because the electronic pair is 100% dislocated by resonance in the carbonyl. So the only way to create a salt is in the extra carboxylate that we have here. In the terminal part, this carboxylate, that has a negative charge. And one says, well, if I want to do an injectable penicillin, because it used to be very common, that penicillin was injected for amygdala Today, the most common thing is to give amoxicillin, which is by oral way, but the effectiveness of this was super high. Injectable, a pinch of penicillin. Yes, it was quite painful. Intramuscular, in the buttocks. The injection was put, and it was painful, because this is little soluble in water. It was like injecting small crystals in the muscle. It is very good. Yes. It is very effective. Of course, it is very effective. And it avoids that one has to be consuming something, because the injection, one forgets rest, and this is super fast. So look, for example, an alternative would be to have the sodium salt. But what is the problem? A hypersensitive could not be pinched with this because we are adding sodium to the sodium plasma. The sodium raises the blood pressure. So someone can say, well, let's inject the potassium penicillin. Of course, there we would have the problem. What happens at heart level with a lot of potassium? The plasma can also produce bradycardia. Also, second is more expensive. And third, the potassium penicillin is more soluble than sodium, and the effect would be less sustained. In time, that is, there would be a peak of effect. That would go down quickly. Then someone thought of this. Someone said, well, why don't we form an organic salt? And we have this molecule as contration. And this has here a benzene ring that can be seen as a means benzene, okay? Benzene and benzene? Well, this is called benzathine. Exactly. Then there is nothing else than a name of salt. I did not say which one is the what. Why give it the mole? And why bother to put this contration so rare? In fact, a benzathine serves for 2 penicillins, because here I have charge plus 1 that complements this negative, and I have 1 left that would go to another penicillin. Well, the grace is that this organic salt is super insoluble in water, and the deposit remains in the muscle, and it is slowly released to the plasma, and it has an effect that lasts up to 2 weeks, or a little more. Then, that is the grace. That is retained there. It is more lipophilic. It is a lipophilic salt. That is the particularity. So thanks for the observation, yes, because this is triggered. Sometimes one thinks that putting a sodium chloride or whatever gives the same. If one already has them, no, the salts have properties. A little different. Getting to the closing of the first block, blue, we go back to the point. We had then carboxylic acid, neutral amine, and an ester that brings little. About the ester, I also want to say something very brief. Here it says ester. The esters bring the truth. Quite little in reality to solubility. Here it says that up to 3 carbon actually. I would leave them in parentheses because that will depend a lot on the chemical environment. So please, the esters, better do not consider them in this list, in an exercise or something that we have to solve. No, the contribution they make is paramount. I think they are overrated to be here, saying that they are able to solubilize 3 carbon. I think no, the esters they are very little soluble. The contribution is very little when there is another functional group, or another ester, since there should be at least 2, or accompanied by another group, there they add more. They add strength, but that alone is very little. What they add, look for example. There's a molecule that we occupy a lot in the laboratory, that is this. And it is an ester. This is the acetyl acetate, right? It takes up a lot. And there the acetyl acetate is soluble in water. No, this is hydrophobic. It takes up a lot of extractions. And it has an ester. It has few carbon. Of course it has 1. It has 4 carbon, but it has 0 soluble in water. It is super lipophilic. Then one says, where is the contribution, even if it was a little soluble? No, this is super lipophilic. That's why I think the esters are overrated. Or the esters there on that list. we are going to say something important, yes, to culminate today on the ester. And with this I finish, is that in medical chemistry, the esters have been widely used in the formulation of propharmacists. Exactly, just like that. So very common. What? Example 1. If you have a drug of alcohol structure, you transform it into propharmacist, adding or making it react with a respective acid. And we are going to have, therefore, the ester-shaped structure. So it is masked. Do not forget the first part. It is the pharmacist part. So I'm going to mark in green the drug of interest. And now, here it is masked. And the process is going to be reversed at the cellular level, biologically, because there are enzymes in the plasma. In the blood plasma, there are enzymes called esters. There are plasma esters and there are hepatic esters. And precisely what they do is break the esters. So by breaking there, we regenerate alcohol within the organism. The other strategy, the degree of hydrolysis, yes, of course. If that is a good observation, later we could place real examples. This one here. It also breaks by this arasa, but the acetylsalicylic acid is quite effective in quickly reaching the nucleoxygenases, where acetylecobalin, that is, the same cyclooxygenase attacks, so to speak, the ester of the acetylsalicylic acid, and is acetylecobalin and that way inhibited. Okay then, of course, not everyone has the same degradation pharmacokinetics. Not because something is an ester, it means that it is going to degrade. So it is a very good example of aspirin. Otherwise, aspirin would not serve at all. It would be degraded, and the cyclooxygenase would not arrive. Another example, apart from aspirin, there is the case of dihydropyridines. Dihydropyridines have two esters, and as esters are active, they are not propharmacists. Then one says, but the arasa esters do not break it. Yes, there is a percentage that degrades, but there is another percentage that remains and manages to reach to the calcium channel, which is where they act. I know it does not mean that, because something is ester. Necessary and mandatory is a propharmacist. So be careful with that. And the last way is that you have that the drug of interest is a carboxylic acid. So if your drug is a carboxylic acid, it makes it react with alcohol to form the ester. Well, and here I am entering the detail of the reaction. Well, all this part is the drug. So now, here is the drug. What is this reaction called? Does anyone remember at a chemical level? When one transforms an alcohol or an acid in an ester, esterification of air. Well, esterification of the ester is a chemical reaction. Well, esterification of bija. Very well, we go from alcohol to acid or from acid to ester. In both cases, that is, from alcohol to ester or from acid to ester. In both cases, then in green is the drug. In blue is the drug. It serves both to transform an alcohol into a propharmacist as an acid.